Hello, everyone, and welcome to today's webinar. My name is Carmen Guguta, and I'm your usual host from Technobis Crystallization Systems. Today's webinar, entitled Controlled Evaporative Crystallization Screening and Enhancing Morphology, is brought to you with the help of our presenter today, Nicolás Ramos Ojeda from KIT. But just before we start, I would like to give you a bit of technical information, as I always call it. The webinar will last about 45 minutes, including questions. Questions we would take at the end of this webinar. I will read through all your questions. Please feel free to use the chat function of this platform to send us your question. Also, if you have any questions afterwards, you can write to us at info@crystallizationsystems.com or directly to Nicolás. The webinar is being recorded and it will be made available to you most probably tomorrow or beginning of next week. You'll receive an email where you can find the recording on our website or on the YouTube channel of Technobis Crystallization Systems. The same in our database publications library, you will find the slides that Nicolás is presenting today with all of you. Just before we start, for those that do not know that well, Technobis Crystallization Systems, we are a Dutch company located in the north of the Netherlands, in Alkmaar. We are a world-leading technology provider for solid-state research, process development, and formulation. In our portfolio, we have 3 products: the Crystal Breather, Crystal 16, and the Crystalline instrument. Some of you might already know the Crystal, all 3 of them, or the Crystal 16 or the Crystalline. If you think after this webinar that you would like to test, to demo one of these instruments in your lab, please feel free to contact us. The easiest way is via the website directly, or just write to me or at info@crystallizationsystems.com. Please remember, the Crystal Breather is the instrument that works at the microliter scale, 32 reactors. It comes with multiple gadgets for controlled evaporation, vapor diffusion type of crystallization. Is your instrument to grow single crystals. The Crystal 16 is your multiple reactor systems with, as it says in the name, 16 reactors working in parallel in 4 temperature zones. Is your instrument for solubility, metastable zone width, induction time measurements, nucleation. There are quite a lot of articles, publications out there where the use of this instrument was emphasized. And the crystal, and it works at up to 1 milliliter scale, so the well-known HPLC vials. Crystalline instrument, it works with 8 reactors in parallel, 8 temperature zones, works at 2.5 to 5 milliliter scale. Is your instrument for process crystallization, process development, formulation. Once you are ready to optimize your process and to bring it to a higher scale, Crystalline can help you to do that. With the camera technology, this instrument comes with a camera technology. It really gives you the eyes on what is happening in the vial. And the cameras work exactly like a microscope. We have different magnifications cameras that they go very close to the nanoscale, but also can give you also ideas of the particle size distribution, shape. Newly launched last year, sorry, the new software package based on AI particle detection and particle size analysis. Also, if you have a Raman spectrometer and you would like to connect it to the Crystalline, it is possible. You can perform reactions or follow chemical reactions or polymorphic transformations, as you would also do with a probe. But in this case, you will do this type of experiment through the vial. So Once again, if you think that one of these instruments is of use for you and you would like to test it further, please try to contact us via the website. And this is a bit in short about Technobis and crystallization systems. And now we come to our speaker today, Nicolás Ramos Ojeda. He is currently finishing his PhD at KIT in Germany at the Institute of Thermal Process Engineering. He has a master's degree in chemical engineering from the Technical University Federico Santa Maria in Chile, with his thesis finalized at Hamburg University. Since 2018, Nicolás has been a research associate at KIT, working under the supervision of Professor Matthias Kind. Over this period, he also had a 3-year cooperation on the evaporative crystallization of API for controlling its crystal morphology with Roche in Basel. Nicolás is also trained in polymorphism, Raman spectroscopy, and protein crystallization. Earlier, he was a project engineer, worked as project engineer on lithium carbonate crystallization studies in Chile, also at Evonik in Germany. Nicolás, I think I will stop now my sharing, and you can share your slide. Welcome to this webinar, and thank you very much for sharing your experience and knowledge today with our attendees for this webinar.
Yeah, thank you for the kind introduction. Okay, I will share my presentation. So you see right now my desktop, and you should see now the slides. Yep.
Yeah.
Perfect. As I was already presented, I'm a research associate at Karlsruhe Institute of Technology, and of course, I am pleased to talk about one of the many topics that are actively researched in the crystallization of APIs, and specifically the crystal morphology, the ways to understand it and manipulate it. So first of all, I would like to introduce the context in which are we immersed when we talk about APIs and its link with the crystallization. For example, just to give some numbers, in the past 5 years, almost 350 new APIs have been introduced to the market. And what the most of the people don't know is that to obtain one single successful API, you need something like 5 up to 10,000 substances, which were actually not able to progress further. And the crystallization takes place roughly in almost 90% of the production of the APIs. So what I'm trying to say here in this slide is I want to illustrate the immense scope and relevancy of the role of the crystallization in pharmaceutical manufacturing. And there are a lot of topics that are currently researched, but I focus during my PhD studies in the crystal morphology. And very rough to say, the crystal morphology refers to the external shape of a crystal. As we can see here, acicular crystals or needle-like and isometric crystal. It's the same molecule, it's the same polymorph, they just differ in how they look externally. And it's just not an aesthetical issue, and they affect the product properties, the processability, like the filterability, tableting performance, and of course, the end-use performance, like the bioavailability. And usually, needle-like morphologies are undesired, while isometric shapes are favored because they exhibit superior performance in the mentioned aspect here. And the typical question when someone is working with crystalline APIs, okay, how can we shift the crystal morphology from this undesired morphology to this one? And of course, there is a lot of research from long years ago, in which we know that the supersaturation, the temperature, solvent choice, and another variables can impact the crystal morphology, and we can get better crystals. In order to address quantitative the crystal morphology, along all the presentation, I will focus on the aspect ratio. It's just the coefficient between the longest and shortest axis if we circumscribe an ellipse in a crystal when we had a microscopic picture. So aspect ratio closer to 1, there is an isometric morphology. If they tend to bigger values, then we are talking about acicular crystal or needle-like. Then in simple terms, the question is, okay, can we reduce the aspect ratio of an API in solution crystallization? And that was the motivation during this already mentioned research cooperation with the company Hoffman La Roche. And if you have interest, it's what I'm going to address in this webinar, but also there are 2 already publications available online, so you can find all the details that maybe I have not the time to mention here. So as the saying says, if ain't broke it, then don't fix it. So the reference system that I get were not perfect isometric crystal. I got 3 different small APIs exhibiting a distinct needle-like morphology, as you can see here. And the goal is to try to shift the morphology of this crystal to more equal shaped crystals. The conditions that we know from their patents were actually not very specific. Those APIs were crystallized via Curing crystallization, and this is all the information that we can get. So right now I'm going to go further where the experimental setup, and first of all, I think we need to see what we have to consider when we are working with APIs, very specific, in which you have less amounts of available material. And how can we optimize this very less material to obtain enough results able to perform a good screening and maybe hit the conditions that promote better morphologies. So we want to use, first of all, experimental setup that mirrors standard crystallizers. We believe that in this way, we can increase the likelihood of achieving consistent crystal morphology at large scales under identical process conditions. A first step, we want to have a clear dependency of the process conditions and its correlation with the crystal morphology. And we want to analyze the effect of the temperature and the supersaturation profile on the crystal morphology independently from each other. To achieve this, we planned isothermal evaporative crystallization. A fourth issue that we want to make sure that we can fulfill is the morphology check. We want to perform that during the crystallization because otherwise the crystals that we obtain could be affected by sampling of solid liquid separation, and we cannot link correctly the process conditions with the crystal morphology. And a final step is a reliable method for measuring crystallization kinetics, but this topic will not be addressed during this webinar. So based on the previous considerations, we had identified crystalline as an ideal platform for our experiments. And what allowed crystalline is that we can work with small quantities of APIs. It resembles typical crystallizers. And what we had done, we had enhanced or augmented crystalline with additional capabilities to enable controlled evaporative crystallization. So as you can see here in the illustration, we employ a stripping gas, and this stripping gas enters the vial immersed in the crystalline cell and evaporates the solvent and exits the system by means of a vacuum pump controlled with a vacuum pressure controller. And of course, you have all the typical measuring technique built in by crystalline, temperature control, steering control, image analysis, and transmissivity measurement. Another case or another scenario that we could explore is to proceed about the stripping gas and just boil the solution that we had here. But this concept with the stripping gas is much better, because otherwise, if we boil the solution, the size of the bubbles will be so large that they could abandon the system and you will not have any reliable measurements. So we have now our reference systems, the experimental setup that I use during these studies. And it's time now to focus on the experimental workflow, how we proceed to obtain more equine-shaped crystals. And as you might have experienced, crystallization data for very specific APIs might not be always available. So in our workflow, we had incorporated these very preliminary steps like solvent selection and the construction of the phase diagrams. And by following that, we create the experimental design, perform the evaporation crystallization experiments, and afterwards the evaluation of the crystal morphology and the polymorphisms or crystal form. If we identify process conditions that desire equine-shaped crystals, then we can proceed to evaluate the feasibility of upscaling. So during this presentation, as we are exploring each step, we will see the results of the application of this workflow. And it might take some time to arrive to the maybe more interesting points, like 5 and 6. But all the steps provide valuable insights that you might consider in your next screening. So for the solvent selection, while the universe of solvents is quite vast, practical considerations narrow down our choice to a select group, typically around 40 solvents, which complies with hazard and operational guidelines. From this initial list, depending on how much data you have available, you can perform some singular solubility measurements, maybe computationally or experimentally. And the first list of solvents reduced to approximately 10 solvents. And next, to get a final set of solvent that will be tested in our evaporative crystallization experiments, we use a solvent chart proposed 15 years ago by Alesso, in which you had a chart of possible solvents. You can picture that like a square. And if you had solvents positioned in opposite corners, that will be the highest degree of dissimilarity. So we select the solvent based on this degree of dissimilarity. In that way, we believe that the interactions between the API and the solvent will be very different among the solvents that we selected, and it could impact the crystal morphology. To build the phase diagrams, we utilize crystalline as well. And we apply, in particular, the polythermal variation method. So you see here the temperature over the time. And what you can see is just successive cooling and heating cycles. So in this way, when the solution or the suspension get completely clear, I mean, all the solids are dissolved, then you have the clear points that are correlated with the solubility temperature. So you can average this temperature, and doing so for all the mass compositions that you need, and you had the solubility curve for the API in the respective solvent. On the other hand, when you gather or when you plot all the cloud points, they follow, of course, an stochastically behavior. And just by linking the minimum undercooling temperature, then you can get an approximated metastable zone limit. So we efficiently construct accurate phase diagrams for each API in each targeted solvent. And in this way, we can now design the experiments or the crystallization routes that we are going to test in each pair of API and solvent. So refreshing the first slide, we had already seen that several variables can impact the crystal morphology. And in our experimental design, we focus on the solvent, the temperature, the supersaturation profile or buildup, and the use of seeding crystal. So a closer look of the specific for the first API shows 4 different solvents, a temperature range within 15 and 55 Celsius degrees, slow and fast supersaturation buildup, and with and without seeding. So exemplary for the first API in ethanol, we can see here the routes that we planned. And as you can see, we intentionally operate with slightly supersaturated solutions, not starting exactly on the equilibrium line. And this decision was influenced by practical constraints. We started each experiment with 5 milliliter volume, and we need to ensure a sufficient remaining volume during and after the evaporation. So in the best scenario, at the end, we still had volumes above 2.5 milliliter, and extreme case, still about 1.5 milliliter. Otherwise, the measuring technique and image acquisition offered by crystalline would not be reliable. So we aim to surpass the metastomical limit, and of course, if we perform a slow and fast supersaturation buildup, then to reach a certain supersaturation, you have 2 different trajectories. So here's the mass loading over the time, or the supersaturation, and in this first case, we evaporate the half of the solvent in 60 minutes, and in the second case, we evaporate the half of the solvent in 3 hours and a half. So these variables, tau 50%, is a very relevant variable because we can apply not just for our experiments in crystalline, but also for our experiments in the large scale. So if we want to have a similar supersaturation profile in the large scale, we just focus to have the same evaporation time to evaporate the half of the solvent. Of course, this variable we cannot set in crystalline, or we cannot just insert, okay, 60 minutes is the time that we want to evaporate. First of all, we need to understand how we get the corresponding evaporation rate to reach those evaporation times. So assuming that we start with a volume of 5 milliliters, we plot an operation curve. And from this evaporation curve, we can read, okay, if we want to evaporate the half of the solvent in 3.5 hours, then we need an evaporation rate like 10 milligram per minute. If we want to evaporate fast, like in 1 hour, then we need an evaporation rate of 55 milligram per minute. And the dependency of the evaporation rate can be well understood just by picturing a crystalline vial and the involved variables. All the geometries are, of course, fixed. We perform isothermal evaporative crystallization, so the temperature is also constant. The pressure is controlled by the vacuum pump, and we had only one variable that is free to obtain different evaporation rates, and that's the volumetric flow of the stripping gas. So for each solvent and temperature combination, we construct calibration curves. One simple method involves just weighting the mass at the start and at the end of the defined period of time to determine the evaporation rate. And these experimental points then can be modeled using a power law, which is in agreement with early literature, as you can find here if you are interested. So we can find now, okay, which are the volumetric flow that we need to get the evaporation rates that we were looking for in the previous slide. Of course, these calibration curves were measured with pure solvent, but still there is a very good agreement from the evaporation rates that were measured from crystallization experiments. And now we arrive to the more interesting part of this presentation, that is the impact of the factors that we select on the crystal morphology. And in this first slide is the effect of the supersaturation profile. Here's the supersaturation over the time. So it's the fast evaporation, the slow evaporation, and so it's how the crystal looks. So in the fast evaporation, it is a marked needle-like morphology, and on the other hand, with the slow evaporation, we get these nice isometric crystals, which were well illustrated by the quantitative analysis of the aspect ratio. Here is the cumulative frequency and the relative frequency, and we'll see that the cumulative frequency in this case tend to values going to 1. And additionally, we took some steps to ensure that the observed change in crystal morphology were not attributed to the crystallization of another polymorph. And as you can see, the X-ray diffraction spectrum correspond closely to that of the stable polymorph A, which is also our raw material. And these verifications provides confidence that the alterations in crystal morphology are indeed attributed to the manipulation of the supersaturation profile. So probably you have noticed from the previous slide here that the nucleation start with the fast evaporation and the slow evaporation happens at different supersaturation levels. So we plot replicates of the experiments. The white boxes are the case with the evaporation performed slowly, and the red squares is when we perform experiments with a fast evaporation. So first, the fast evaporation had a higher variability and promote the nucleation onset to higher supersaturations, which is not the case when we perform the evaporation at a slow evaporation rate. And secondly, there is a clear trend on the median aspect ratio in dependency with the supersaturation at the moment of the nucleation. So this API is particularly high dependent on the supersaturation, the morphology of this API. So higher supersaturations promote the formation of needle-like crystal, explaining the behavior observed before on the pictures that we saw before. And so we can plot the cumulative frequency of the aspect ratio versus all the factors that we tested. In this case, is the temperature effect. So we see that at higher temperatures, we get isometric crystal. This is not the case, for example, at 15 and 50 Celsius degree, we get more elongated crystals. We can see that, for example, in isopropanol, although we perform a slow evaporation, still we were not able to get isometric crystals. And we highlight, as other publications, how powerful is the effect of seeding. So we had this experiment performed just with spontaneous nucleation. And in the case that we add some seed crystals, we get again very nice isometric crystals. And in all those experiments, after X-ray diffraction analysis, polymorph A was the crystal that was present on the samples. And it's important to note that these results were not limited just to this first API. For the second API, we also moved this very acicular morphology to more equal shape crystals. And we observe the same for this third API. So These results shows how this rational workflow for studying the crystal morphology is able to improve the crystal morphology or to at least to find process conditions that improve the crystal morphology. It was an error selection of solvents, and we exploit the capability of the evaporation so we can perform experiments at very higher temperatures. And all those are features that we would like to highlight from our workflow. So the first remarks of this first section of my presentation is that we had a useful tool for screening and anxiety aspect ratio, and a difference of at least one order of magnitude in the median aspect ratio between the worst and best case were observed. And we fulfill all the considerations that we had at the beginning: an efficient usage of raw material. We had an unmistakable assessment of the crystal morphology with the process conditions. And thanks to the geometry or to the characteristic of crystalline, we believe that it facilitates the transferability for at scaling. And this is the next part of my presentation. It will not be so extensive like the first one, because right now it's just one point, just the results in the Lita scale. You can also visit the publication with the details. And we performed this experiment because all the results necessitate the validation on a large scale. And the at-scaling process is to be tested in a liter-scale crystallizator, which represents a significant 200-fold increase in scale. So if we compare visually the difference on both scales, here's a typical vial of crystalline, and that will be the volume by performing an experiment in the liter scale. And we got careful consideration to the selection of system dimensions in both systems, trying to closely match, for example, the diameter of the crystallizator in relation to the diameter of the stirrer, the level height in relation to the height of the stirrer, and that kind of geometrical considerations. Constant stirrer speed was the chosen criterion to have similar mixing behavior. We are aware that some more complex approaches can be employed, but our primary goal is to study the transferability of this first intermediate scale, and further studies can be surely might be more valuable by scaling to a more large scale. The Lita scale experimental setup is an stirrer crystallizer with a double wall glass. The system pressure and boiling temperature were regulated by the vacuum pan integrated controller. Sorry, I see a hand here. That's somewhat a question.
Nicolás, I would say I see two hands up, but let's take them at the end of the.
Okay.
Yes.
I was just thinking that it was maybe because of a connection issue, or that you cannot hear me. Okay.
I think there are questions, but we will take them. I will try in the system, although it's my first time, to give voice to each one of them once it is. Yeah.
Just making sure that no communications or connection issues are during the presentation. Thanks, Carmen.
Thank you.
And so that's, as I was saying, the vacuum dropped right here. So control the vacuum pressure in the crystallizer. Unlike the miniaturized crystallizer of crystalline, we are not using a stripping gas. Now we had a large volume, so we can perform a normal evaporative crystallization. The thermostat here controls the temperature on the jacket, and therefore the evaporation rate that we try to set at a temperature in such a way that the evaporation rate provides the same supersaturation willout as the one observed in the milliliter scale. Turbidity measurement was also present, and a second difference is that we don't have inline assessment of the crystal morphology. So we need to sample suspension of the crystallizer, and in order to have the same octet, those samples were placed in crystalline to assess the crystal morphology. So will it look the landscape of possible crystal morphologies that we get from the miniaturized scale. And in order to demonstrate the transferability of the process conditions in the large scale, we selected case yielding isometric crystal, but also one case yielding needle rock-like crystals. So if we revisit those cases, for example, case 1, we can see here how the crystal were looking in crystalline. It is a low aspect ratio between 1.6 up to 1.9. And in the other case, it is a clearly more rock-like elongated crystal morphology. You can see also this offline and inline curves, because if you are interested to perform those experiments in large scale, you are not only interested that during the crystallization inline, the crystal had the targeted morphology, but after the solid liquid separation and after the drying, that this morphology remains. That's why we perform those analyses offline and inline. And there is a quite good agreement between both curves. Now, regarding the process resemblance, here is the supersaturation over the time for the liter scale and the milliliter scale. And overall, the supersaturation will have succeeded under very similar conditions at both scales. There are only significant difference in the supersaturation level at the moment of the nucleation onset, which is not a rare phenomenon. It has been evidenced in several studies. If you are interested in one of them, you can visit this publication. And we need to take this into account when we analyze the crystal morphology after the crystallization and during the crystallization. Now is the comparison between the scales. So we have the experiments with the continuous line for the milliliter scale and the segmented line for the liter scale. Here's the aspect ratio. And as you can see, there is a very lower variability on the aspect ratio. So we get, we can say that we get very equal shaped crystals in the milliliter scale and in the liter scale. Regarding the width, we can also see that at least during the crystallization, they had very similar dimensions. And there is only a slight difference after drying in the milliliter scale at the liter scale. And now regarding the length, we can see that the elongation along the length of the crystals, it is very significant in the liter scale. And we can attribute this to pure filtration, maybe resulting in rapid evaporation of the mother liquor and promoting a circular growth. Now for the case trying to crystallize needle crystals, again, the variability on the aspect ratio can be seen in both cases, but still, at least during the crystallization, they tend to be more equivalent, and it happens exactly the same after drying. But here's the issue that that it was more noticeable after the experiments. So the crystal length in the liter scale after the filtration and drying, it is more or it's much longer in comparison to the milliliter scale. So we believe that this suggests that the large volume of the liter scale crystallizator reduce the likelihood of crystal breakage compared with the milliliter scale, and that might explain this difference. So I think I will wrap up the presentation for the sake of time. For the second section, we can also say that we achieved the same crystal morphology on much larger scales. So we were successful in keeping in overall the same morphology, but the variations in crystal size expose expected issues influenced by spontaneous nucleation and agitation regimes that were not entirely equivalent. But this insight becomes more crucial for future scaling up steps, and in those endeavors, for sure, more meticulous control over this aspect should be undertaken. And finally, I think this is the key take message from this second part, is for sure we provide more certainties that experiments from miniaturized crystallizers are in large extent consistent with the outcomes on large scales. So I thank you for listening. The company for Hotman LaRoche for its sponsorship, to my supervisor, Professor Matthias Kien, or my colleagues during my PhD time, or the students that were working in this research, and of course the specialists from Technobis, that they were always available to discuss and figure out some technological aspect that we could apply to perform this research.
Thank you very much, Nicolás. Thank you for sharing your research and experience with us. I will try to do something I haven't done up to now, to be sincere. So all please have a bit of patience with me. I'm trying to give the words to allow, because usually the attendees are in listen-only mode, but I see those hands raised. So I'm not very sure if I read your name correctly, Micheline Marquet. I think now you are allowed to talk. You could ask your question. Oh. Do you hear us? Can you... Yeah, I do not hear anything. I will try it once again. Do you hear us, Micheline? No. I'm not very sure if it works. I have marked this person with... Oh, now it's gone. To be able to talk. Allow to talk. Once again, let's see. Now it's kind of like thinking. You should be able to talk to us. No. If not, could you please write your question in the Q&A? Then I can read it for you. In the meantime, I had a question, Nicolás, because you have mentioned about this evaporation. For my understanding, how did you modify this flow evaporation fast and slow in the crystalline? It was by making use of different flow, volume, pressure, or have you used physically something else next to what it was delivered, or what was the engineering?
Yeah, I think you can see here just the abstraction. So we had a mass flow controller. Yeah. Maybe I will try to find slide how that looks at the laboratory.
Okay.
So you had here the mass flow controllers, which
Okay.
are connected to crystalline.
Uh-huh.
So you have to control that externally. And in that way, you had a controlled evaporation rate.
Yes.
And as I said before, all the other variables are constant. So it's the only variable that I'm changing during all this experiment. The pressure, the vacuum pressure, what's fixed at the very beginning, etc. In some preliminary experiments. Yeah.
Okay. And then you also had something related to you said when you also went to higher scale that you have measured inline and offline, this aspect ratio. Inline, I guess, with the probe or in the bigger scale, but
yeah, in the milliliter scale, I mean, in the crystalline device, is for sure not quite challenging. You had the image of crystalline with the cameras.
Okay, so
and then in the liter scale, we were limited. We don't have a zone to explore that inline. But what we tried is to take the samples at the same conditions, keeping the temperature constant, place the suspension in a crystalline vial, and those vials immersed in crystalline exact at the same temperature.
But the measurement with the crystalline, of course, I know this, it's from the, you can do it on the pictures, but I think for the crystalline version 1 that I saw in your picture, I'm not very sure if now, if this, you have taken the data and calculated separately, right?
Yeah. We need to develop or to write a separate script. We write that in MATLAB, and it's just use all the exported image from crystalline, and it performs the analysis of the aspect ratio.
Okay. Because we do have something now in the second version of the crystalline that was launched and in the software, and it just popped up to me because recently I visited a customer and we were discussing about this aspect ratio that is now available, but I saw the picture of the V1, so that's why it triggered me. Okay, I read a few questions to you. I see Katie. She was asking, how did you physically connect the MFCs inside the crystalline?
The what? Sorry, I didn't understand the
MFCs. If you look at the questions, the Q&A, it's from Katie Foster.
Yeah, I will.
Oh, it's.
I just stopped my presentation so I can. Okay.
Do you see it?
Okay. How do you speak like names?
How did you physically connect the MFC?
The mass flow controllers.
Yes. Oh, yes.
I will start to share my presentation again.
Yeah.
Sorry, probably I could. Okay. Yeah, you have two options. You can use this very robust pies from Swaklot exemplary, but we perform so much experiments that we choose to use chemical compatible hose. So here maybe you cannot see very well, but there is a nozzle going out from the from the mass flow controller. It doesn't have the diameter that you can put into a crystalline vial, so you have to use some joint parts, and those joint parts can decrease the diameter for the next hose, and at some points it has the proper diameter to be attached to the lid of a crystalline vial. And this vial, it will look Let me see. Like this. So you just need to ensure that the final host had exactly a diameter that you just can put here inside. Or actually just like enveloping the nozzle in the crystalline lid. And this is a special lid from Technobis. It has 4 openings. Yeah, one for the inlet of extruding gas, for the outlet, for the use of seeding, and for the measurement of the temperature inside the solution or suspension, because when you are evaporating, you have a cooling effect.
Yeah. Another question, Nicolás. When increasing the flow rate, it is increasing the supersaturation and consequently the nucleation rate?
When increasing the flow rate, it's increasing the supersaturation and consequently the nucleation. I mean, when we are increasing the flow rate, we increase just how is the supersaturation will up. And then at the moment that it nucleates, it will nucleate faster because you are just driving the supersaturation faster in comparison to the other case. So it will be dynamic. The supersaturation will ascend faster in comparison to the other case.
Thank you. Let me take it systematically from the very beginning, then we are not confused. So one of the first questions, are there options to do basic slow evaporation with the presented setup in the Crystal 16? I will take that one. No, indeed. The Crystal 16 is our only instrument that doesn't have this possibility of using the evaporation. With the Crystal Reader, you can do controlled evaporation if you connect it to a vacuum pump. With the Crystalline, you can, but not with the Crystal 16, and also because there are no caps. You also need specific caps to be developed for it. You never know, maybe in the future, an idea for our colleagues from technology development. Thank you for the beautiful presentation. Please, can the slides and recording be shared? Yes, the recording will be shared in an email with all of you. You will see on our YouTube channel or our website the recording quite soon, I think tomorrow or the latest on Monday. The slides, Nicolás, I think you said you will share with us, and we will be able to upload them on our website in our database, and also you'll see a link in our email following this webinar. This I did. Dear Nicolás, is this Technobis system continuous in your experimental design, or do you take the samples and measure in a different place?
I'm not sure if I get which experimental setup is meant, but if it is mean the operation is not continuous, it's batch crystallization, yeah.
Yes.
And the samples, as I said before, in the experiments performed in crystallines, then is everything performed and measured in crystalline. Just the analysis are performed after the experiments with a separate script. Yeah.
Or if it was related to the aspect ratio, maybe it's there.
Yeah, I mean the samples after the crystallization, yeah, that were for sure measured offline.
Yeah. Well, the pictures are taken on continuously, but then you will analyze offline.
Yeah, the pictures are taken continuously, normally with an image rate acquisition of 5 seconds. So we got plenty of pictures during the whole experiment.
Yeah. And indeed, this with the first version of the crystalline, you need to do something additional to be able to get that information out. But I think the latest release of the software for the V2, for the second version of the crystalline. It's already implemented in the software. I would be actually interested, Nicolás, because I think this is also a publication, to see exactly if what we have implemented in the back side of the software resembles at least, or it has the same mathematical model what you were using. Maybe we could adapt.
Do you mean in the image analysis
Yes.
script?
Yeah.
I mean, it follows the typical steps. I'm not sure if you can see my presentation.
Yes. Yeah.
Okay, so maybe it's so this is the route image, and then you had a segmentation based on the illumination of the picture. Then for all those small segments, you had the background removal, the binarization, and after that it will be construct the perimeter of the crystals, and then with a circumscribed ellipse you had the X max, I mean the length and the width of the crystal.
Yeah, no, the same is now in the exactly the same is in the version 3. Another question, Nicolás. For scale-up experiments in crystallization / polymorph preparation, what kind of variables you faced for consideration during your experiments? Merely do multiply factor works to scale up from milligram scale to gram scale to kilogram scale? It's just before the message from Katie saying thank you.
Yeah, for scale experiments. Yeah, in our case, I presented before 3 different APIs, and we selected for the experiments with upscaling, of course, the most generous API that it didn't show any polymorphisms within the temperature range that we were working. So in that way, we just have to focus, okay, we need to just perform the same supersaturation, wield up, just keep the temperature, the same solvent, and we don't have, so we try to do not have those issues, because that will make the whole problem complex in the validation. But for sure, then it will not be so so simple, the API. Then you have to consider, okay, how will affect this new large system the nucleation at with supersaturation level it will happen, and maybe you get another polymorph, what was not observed before in the miniaturized scale.
Thank you. One more question. What are the situations that justify using evaporative crystallization over cooling crystallization? Your thoughts about evaporation versus cooling?
Because I cannot cover all the details of the APIs. I think it was slide, something like that. Okay. For example, this API, it had polymorphs, so it behaves differently at certain temperatures. So if we perform some temperature program going above a certain temperature, then we can crystallize a polymorph that we don't want to have. So by doing evaporative crystallization, we had a new degree of freedom to have the temperature constant, and exactly at that temperature oversaturate the solution.
Okay, thank you. Iman, I see your hand is still raised, but I think we have just answered his question. Micheline, you still didn't write to us. I allowed you to ask the question, but I don't know, I think you can still not make use of this function, please write to us at info@crystallizationsystems.com or directly to Nicolás. We would be able to help you further. Katie, thank you for your questions. If you have more questions about this setup of the mass flow with the crystalline, I know you are a super user of ours of the crystalline, and if we can help you further, we can also put you in contact also with Nicolás, but also together with our engineers to help you to build up such a setup. Further, I think we have addressed all the questions. Thank you very much once again, Nicolás, for bringing this piece of science, information, knowledge, and your experience, both with our instrument, but also related to evaporative crystallization, and also bringing it to a different scale up. Thank you very much. And we will share soon the slides and the recording.
Thank you for the opportunity to present my results. I try to address all the questions as I understood it. So if you had further questions, follow-up questions, just write me. You can find my information on the website of Crystalline during the advertising of this webinar. Probably you can also find me if you Google me.
Yeah, or we can, if you agree, if somebody asks for your email address,
no problem.
Okay, perfect. Then we directly forward you the questions. Once again, thank you very much. Thank you all for joining us today. Next month, we are launching a new line product, a new product addressing reaction chemistry. Something new for Technobis, a new adventure. Hope to see you all there as well. Let your colleagues know if they are busy with synthesis and reaction chemistry. Thank you and have a good evening or morning. Bye.
Bye.